Hi everybody. Today we're going to talk about graphing quadratic functions in vertex form. So we've already looked at quadratics that have been in standard form. That was when we found the models using our matrices and using explicit and recursive formulas. So today we're going to take a look at when the quadratic is written in vertex form. So what's great about vertex form is that it shows us the shifts in the quadratic. So if we remember back to our first unit, this h is going to shift our quadratic horizontally. Okay, and that k is going to shift our quadratic vertically. So we always want to start with that. That's really great because if I'm going to start at 0 and I'm going to shift something horizontal and vertical, in a quadratic, that's actually going to give me my vertex, h, comma, k. Now that a value is very important in helping us decide what kind of parabola we're going to graph. So now if a is a positive number, meaning that a is greater than 0, this is going to mean that the parabola will be opening up. Now if a is less than 0, that means that the parabola is going to open down. Okay, so a parabola that opens up will look something like this. Okay, it could be in any quadrant, vertex anywhere. If the parabola opened down, it would look something like this. Now, the a value also tells us how wide or steep our parabola is. Okay, now the absolute value of the a value will tell us that, right? Because obviously if a is positive, that means opening up versus opening down. A is negative. So if the absolute value of a is greater than 1, okay, then that's going to make the parabola steep. And if the absolute value of a is some sort of fraction, right, meaning that it's between 0 and 1, some sort of proper fraction, then that's going to make it a little bit wider. So a parabola that is steep could look something like this, awfully skinny, right? And a parabola that is wide would look something like that. So when you look at a graph in vertex form, you look at an equation in vertex form, you're looking for the vertex, which you'll see right away, h and k, and then you're looking at the a value telling you what kind of a shape that parabola is going to be in. So let's take a look at an example. Let's say I have f of x equals 2 times the quantity x minus 4 squared minus 5. All right, so right away, that vertex is h and k. So that's going to the right 4 and down 5. So that vertex is going to be at 4, negative 5 right here. So I'm going to make a table. So I'm going to say that the vertex is going to be in the middle of my table because I'm going to pick some points that are to the left and to the right of the vertex. That way I can get some really nice points for my symmetrical parabola. The great thing is that if I pick the value 3 for x, if I substitute that in, that's going to give me the same y value as if I were to substitute in 5, because our graph's symmetrical. Same thing for 2 and 6. So let's think. If I plug in 3, if I substitute x in for 3, I get 3 minus 4, which is negative 1, squared is 1, times 2 is 2, minus 5 is negative 3. So now I have the point 3, negative 3, and 5, negative 3. Okay. If I plug in 2, or substitute in 2, I get 2 minus 4 is negative 2, squared is 4, times 2 is 8, minus 5 is positive 3. Okay, so my next point is 2, 3, and 6, 3. Okay, now 5 points is a great amount of points to plot when you're graphing a quadratic. Obviously, we've learned in the past that you only need 3 points to determine the quadratic model. Okay, so you could just plot 3 points if you wanted to, but sometimes 5 gives us a better shape. Now you might notice here that in order to get from the vertex to the next lattice point, I just have to go up 2 and over 1. Up 2 and to the right, up 2 and to the left. That's also the same as your a value. Okay, so that might be something that you notice when you're graphing these in class and you're doing some practice. However, this does not work all the time. Okay, so you can't always just go up the a value into the left one or up the a value into the right one. Okay, so you need to be very careful about how you think about that. So now Let's take a look at another example. Maybe we make this one a little bit harder. Let's say that g of x equals negative 1/2 quantity x plus 3 squared plus 4. So your vertex is negative 3, comma 4. So plot that first. Okay, that means that my quadratic is symmetrical over the vertical line through that point. Okay, I could even write that is the line x equals negative 3. That's that vertical line. So when I make my table, okay, we'll put negative 3, comma 4 in the middle. Okay, notice that if I plug in negative 4, that'll be the same as if I were to substitute in negative 2. Same with negative 5 and negative 1. So if I plug in negative 4, I get negative 4 plus 3, which is negative 1. Squared is 1. Times negative 1/2 is negative 1/2. Plus 4 gives me 3.5. Okay, if I substitute in negative 5, negative 5 plus 3 is negative 2. Squared is 4. Times negative 1/2 is negative 2. Plus 4 is 2. Okay, so let's plot those. So I get negative 4, negative 4, 3.5 is here. Then becomes here, negative 5, 2, and negative 1, 2. So we're noticing that this parabola is wide. What you should be noticing is that your a value is negative 1/2. Okay, so that should already tell you that this graph is going to be wide. Now your next lattice point isn't until negative 5, 2, or negative 1, 2. Okay, so be careful about trying to use that a value as a shortcut. Something to note is that parabolas always have absolute extrema, right? So if the parabola opens up, it's going to have an absolute min. If the parabola opens down, it's going to have an absolute max. Something else that's important, of course, is where the parabola crosses the x-axis. So I can see here that it's going to cross the x-axis twice, okay, because my vertex is in quadrant 2 and it's opening down. Now I could probably estimate those zeros if I wanted to, but I might actually want to find them as well. The other important part, where the parabola crosses the y-axis, it looks like it's going to be somewhere down there. Now we can find exactly where the graph crosses the x-axis and where it crosses the y-axis. Okay, so let's figure that out. Now if I want to find the y-intercept, well, we know how to do that, right? Because if a graph crosses the y-axis, that means that that point has an x value of 0. So we'll just substitute 0 for x. Okay, so 0 plus 3, that's 3. Squared is 9. 9 times negative 1/2 is negative 4.5. Plus 4 is negative 1/2. Right? So the y-intercept is 0, comma negative 1/2. Now if I want to find the zeros, right, that's just where the graph crosses the x-axis. Now that means that the y value of those points is 0. Okay, so if I solve that, I subtract 4 from both sides. Okay, then I get rid of the negative 1/2. Now I'm going to square root both sides. Now be careful, right, because the square root of 8 is the square root of 8, but it's also negative square root of 8, right? When you square root something, you should get a plus or minus answer. So in this case, your zeros are negative 3 plus root 8 and negative 3 minus root 8. Okay? Now, this actually gives me a better idea of where my zeros are because I could kind of estimate this if I wanted to. You agree with me that root 8, let's see, that's probably something like 2.8 or maybe 2.9, right? Because 8 is close to 9 and the square root of 9 is 3. So you could kind of say that that's sort of, whoops, something like this. Means my zero is somewhere like around negative 0.1 and somewhere around negative 5.9, something like that. So if I think back to my picture, I think that I'd be correct in saying that those are the right zeros. Okay, but it's plugging in some points, doing some analysis. Okay, everybody, good luck.
This is the definition of my life. Lying in bed in the sunlight, choking on the lemon tablets, come together in the hope of saving me, in the hope of saving me. Marks in the corner of the room, the junkyard full of eyes and gloom. I asked him time again.